Well, actually, I'm going to maybe show you my face. Not that you really care to see my face, but I guess you don't really get a choice. Welcome to the first real kind of lecture. It's a little long, about 50 minutes long, so I'm going to break it into two chunks. For the first part, well, you'll see, it'll be obvious. And so the format's going to be a little different every time, just because where I do this and when I do this is a little different every time. It was just raining out, and so I set up to record inside, but now it's not raining, so I'm recording inside. So here we go. And I thought the last time I gave this particular lecture, I don't know if you remember, but a couple of years ago, so it would have been January of 18, maybe January of 19. It was really cold, and for those of you who live in Wisconsin or lived in Wisconsin, the highs were in the negative 20s, right? The highs were in the negative 20s. And everything you read in the newspaper is like, the polar vortex, the polar vortex. You turn on the news, the polar vortex, right? And it drove me crazy. Because there's always a polar vortex, right? As long as the Earth is spinning, and then so there's high pressure here and low pressure here. The Coriolis accelerations are always going to spin things to the right? So the airflow in the northern hemisphere is always going to go like that. So there's always a polar vortex. What they should have said is big Rossby waves in the polar vortex, right? And it just so happened that in January of 19, we were sucking this cold air down into Wisconsin. So I think the Rossby wave probably went way up here and then brought a bunch of cold air, from way north down to us, and that's what caused it to be so cold, right? Now, and I just like to dispel, oftentimes the media don't really portray science very well. And I always like to say, hey, as mechanical engineers, you'll learn to be critical thinkers. And so related to the polar vortex, you'll learn about stuff like that in ME 240. You'll learn about Coriolis accelerations in 240. You'll learn about thermodynamics, right? How energy changes phase and changes the types of energy that we can track. That's in thermodynamics, 361. ME 363, the best class. Fluid mechanics, you'll learn about how all this stuff flows. Maybe not in spherical coordinates, but you'll learn about fluids. And then, of course, heat transfer has a lot to do with how you feel, right? Oops, wrong page. So anyway, I thought, well, the lectures are Tuesday morning. And so I said, tomorrow morning, the temperature is expected to be minus 27 degrees Fahrenheit, right? And college kids are not known for being especially good decision makers. So I thought, well, let's talk about good decisions. Now, here's a guy. This guy here has really nice hair, right? Sure, his hair is great, right? Look at that. Just perfect. Beard, perfect eyebrows, perfect hair. Right. And so there's a lot of college kids that feel like they shouldn't wear hats. They don't want to wear a hat because they'll mess up their hair. Now, newsflash, you're an engineering student. Nobody cares about your hair, right? Nobody cares. Maybe you, nobody else. And if you don't wear a hat when it's negative 27 degrees, you wind up looking like this guy, right? If you don't wear gloves, you wind up looking like that, right? Now, that doesn't look good, right? This maybe gets you a date. This definitely hurts your chances, right? So 2 years ago, I was saying, hey, make some good decisions. Look outside, look at the environment, make some good decisions. Ironically, a year and a half later, it's also time to look at our environment and make some good decisions. Like, don't go partying with your friends. Don't pack 30 kids into a dorm room, because you're all going to get COVID-19. You may not get sick, you may not feel like you're ill, but then you spread it to old people like me who could die, right? So please make good decisions. All right, so anyway, besides that, let's see what's next. Some course logistics. Actually, I'm going to just show you my face for this, because I know everybody wants to see my face. So a couple things. This is a hybrid class, right? Now, we don't typically teach hybrid classes, but the COVID-19 pandemic has caused us to do this. So the majority of the class is online. Just because you don't have lab one particular week doesn't mean you got the week off, right? Just because Monday happens to be a holiday doesn't mean we take the week off. It doesn't work that way. So typically the, holiday or not, I'm going to put the lecture up on Monday morning. And then we'll have labs on Tuesday, Wednesday, Thursday, face-to-face labs. But to bridge from lecture to lab, you have to do a pre-lab in here somewhere. Whether or not you had lab, whether or not there's a day of the week, whatever, right, you have to do this. And then we'll have labs on Tuesday, Wednesday, Thursday. And then on Friday, right, there's nothing on your schedule, but in a normal semester, we would have lab on Friday. And so this semester, we're going to try to maintain as much normalcy as we can. You still have something to do on Friday. So why do you need to have a pre-lab on Friday? The reason you have to have a pre-lab on Friday is because we want you to figure out what you know and what you don't know and get your question answered. We've got an awesome group of essays all day long on Friday available. I'm available on Friday. So please contact them and ask your questions, and then that'll hopefully get you set up to do well on the lab for the remainder of the week. Right, or the weekend as you work on that. All right. What else? Some other stuff too. Oh yeah, cloud storage. Most of you have done a really good job at that. Many of you have come to me saying, yeah, I got Kumo set up and I got my box drive set up and blah, 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 and they just had a few glitches. For those of you who haven't done that, learn to organize your stuff. And by organize your stuff, I mean your computer files. Don't have a million files all over your desktop. All right, have an ME201 folder and a Math 221 folder and a Math 222 folder and a Physics 201 folder and whatever else. Organize it. Use file names that make sense. Keep it in the cloud somewhere so you can access the information from anywhere you need to. All right. Okay, so that's that. And then, regarding SolidWorks, it doesn't run on a Mac. SolidWorks doesn't run on a Mac. Ease doesn't run on a Mac. A lot of the things we'll use in MATLAB don't run on a Mac. So for those of you Mac users, myself included, please use Citrix and just run this stuff remotely. Even if you use Windows, oftentimes it's just easier to run it all remotely via Citrix. So you're actually operating machines somewhere at 1410 Engineering Drive, even though you're in New Jersey or California or Madison, wherever you are in your apartment. So please use Citrix. It works well. If you want to install the stuff directly on your hard drive, that's fine too. For the Mac users, it's not even an option. So that's that. SolidWorks works much, much better with a 3-button mouse. So you want to go left click, right click, and then the little scrolly guy in the middle. It just works a lot better. So you might consider finding yourself a fully functional mouse rather than just a little finger pad on your laptop. Okay, I think that's it for logistics, yeah. So let's go back to this. Go back to that. All right, so I think we covered all that. All right. So today's topic is resolution and oscilloscopes. I'm going to split that into two. But we'll start with a funny little joke, one of my favorites. Blah, 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 blah. There are this many types of people in the world. Those who understand binary and those who don't. Right? Some of you probably have seen this and you think it's funny. Some of you are seeing it for the first time and you think, oh, that's kind of clever. And there's some of you who are like, what? Right? And so that puts you in the category of those who don't. Right? We live in a very computer-based world, so we need to understand binary, right? And the base 2 number system. So recently, the past few days I've been riding my road bike. Like I've got a pretty nice road bike that I've been riding to school because the rear wheel on my commuter bike is just shot. And so I'm finally ponied up. $103. $103 for the new wheel. Now, you and I, new wheel, right? You and I look at this 103 and we're like, oh, of course I know what that means. It's $103, right? But what does it really mean? This number here is that's wrong. This is 1 times 10 to the 2, right? That is how many hundreds did I have to spend on this new wheel, right? Fortunately, I only had to spend 100 on the new wheel. This number here, right, as we all know, is 0 times 10 to the 1. How many tens? I didn't have to spend any tens. I had to spend 100, which is actually 10 tens, but it's 10 squared. I didn't have to spend any tens. And this spot here is I had to spend 3 times what? Times 10 to the 0, right? So 103 really represents $3, 0, $10, and $100, and that's how I get the cost of my new wheel, right? So if I wanted to do this in binary, in binary, how would we do this? Well, I'm going to do a little sidebar over here. Sidebar. And if you know how to do this right, please skip ahead. I know 2 to the 0 equals 1. 2 to the 1 equals 2. 2 squared equals 4. 2 cubed equals 8. 2 to the 4th equals 16. 2 to the 5th equals 32. And 2 to the 6th equals 64. Right. I'm going to stop there because I know I can get all the way up to $103 just with 2 to the 6th. Right. So I'm going to need at least one of a 64. Right. So 1 times 2 to the 6th. Right. And then I'm going to need a 30. So this is 64. And then I'm going to need at least a 32, right? So that's 1 times 2 to the 5th. So that's a 32. Wow, so I'm getting close already. So I'm already at 96. I need 7 more bucks. So I don't need, so I need one of these. I need one of these. I don't need any of these. How many dollars do I need? I'm at 96. I need 7 more. So I don't need any of these. But I'll need a 4. So I'll need one of those. So that's plus 1 times 2 squared, right? So that's a 4. So what am I at now? I'm at 64, 32 is 96. I'm at 100 so far. So I'm going to need one of these, which is 1 times 2 to the 1st, which is a 2. And then I'll need 1 times 2 to the 0, which is a 1, which means that in binary, if I wanted the cost of this new wheel, it would be 1, 1, 0, 1, 1, 1 dollars, right? Now, this isn't $110,000 wheel, right? This is a $103 wheel. But if we wrote it in binary, it would look like this. Okay, so that's what the binary system looks like. Yeah, so a fun little example there. Okay, and so this brings up an important question that many people of you asked. Is this a electrical engineering class or is this a mechanical engineering class? And this is a totally fair question because we're going to do stuff in engineering equation solver, MATLAB, program Arduinos, do a bunch of stuff like this, make measurements with an oscilloscope. Primarily because the mechanical side of mechanical engineering is fairly intuitive, right? But you're going to design things using computers. You need to know how those computers work. You're going to build things with computer-controlled equipment, right? You need to know how that stuff works. You're going to test them with sensors, right? But you don't. There's no such thing as a temperature sensor, right? It's some device that converts a certain temperature to a certain voltage, and then you have to measure that voltage, right? So we're constantly using electricity and digitally manipulating electricity voltages in order to do our job as mechanical engineers. So that's why we're going to spend a lot of time learning this stuff in this class. All right. So that's that. So yeah, it is. I mean, it's a mechanical engineering class. We're going to do a lot of electrical stuff along the way. Well, speaking of cold weather and changing weather, I thought I'd just give you a quick little overview of my wardrobe, right? And my wardrobe includes, all my different sock collections, right? Wool socks, regular socks, dress socks. I never really wear those. Cycling socks, I wear those once in a while. Gray cotton socks, blah, 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 right? And then everybody has like a sock drawer. Most people have an undies drawer. For the record, I don't think I actually own any tidy whities. They might be hiding deep down in there somewhere, but I'm not even that old. And then, of course, t-shirts, right? And so I've got, my science t-shirts, which I have a surprising number of running t-shirts from different running events, skiing t-shirts from different skiing events. And I've got some a lot of beer t-shirts that I shouldn't wear to college, and then beer t-shirts that are subtle enough I could probably get away with them. Blah, 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 blah. So lots of t-shirts, right? So I've organized this kind of by category so far. Oh, and then there's jeans with holes, and some long, other long pants that I wear at college sometimes, and some jeans that my wife thinks I should throw away, but I'm like, no, those are still good. I'm not going to get rid of those. Fleeces, got lots of fleeces, warm things. Hoodies are going to put that in the same kind of category here. And then other shirts and cycling jerseys, blah, 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 right? So I could organize this in a number of different ways, by shelf, by drawer, by style, by dress up, by color, by whatever. But as an engineer, I got to figure out a way to be more meticulous about this, right? So I'm gonna make myself a 3-bit closet, right? That means my closet has room for 3 binary digits. The 2 to the 0 place, the 2 to the 1 place, and the 2 to the 2 place. So if I fill all of these up, right, I start with 0, right? 0 is all zeros. 1 is 0, 0, 1. 2 is 0, 0, 0, 1, 0, right? Until I go all the way up here to the number 7, which is a 4 plus a 2 plus a 1, right? I add all those things together. So my 8 drawers, right? I could say, well, that's 2 to the 3rd drawers, right? So that means I could label my drawers drawer number 0 all the way up to drawer number 111. I've got 8 drawers, but if I label them with a binary system, I'm going to have 0, 1, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. Those are the labels for my 8 drawers, all right? What's next? Okay, so now I've got 8 drawers to deal with. So I'm going to divide my clothes by temperature, right? That way I don't have to worry about color. I don't have to worry about style. I don't have to worry about fashion, not that I do anyway. I don't have to worry about anything but what's the correct temperature range for this stuff, right? So I put the clothes, let's change this to blue here. So I put my cold clothes here, cold weather. Down here, and then so for those really hot summer days, I put my hot weather clothes up there. So I just look at every article of clothing. I say, what is this? What's the right temperature range for this particular piece of clothing? Understanding that we have layers, and right, the analogy starts to break down. But I'm going to put them in bins like this, right? So one important thing about this. Okay, now keep in mind, right? I'm gonna leave this slide. I'm going to take 0 to 80 degrees, basically, and I'm going to divide them into 0 to 10, 10 to 20, 20 to 30, 30 to 40, 40 to 50, right? So the resolution I have here is if I pull out some, piece of clothing, let's say from the bottom drawer, right? So let's say I pull something out from the bottom drawer. Here we go. Now, I don't actually keep my socks in my desk, my office desk, but here I got a sock, right? It's a nice wool sock, except it does have a big hole in the bottom. So here's a sock. I grabbed this from the bottom drawer, which means I know this sock is good from 0 to 9.99999 degrees, right? That's all I know about it. So I can feel and say, well, yeah, it feels thick. It's actually probably good for, but it's got a hole. No, I can't do that. When I reach into this particular drawer, I only know that it's good for some temperature range between 0 and 10 degrees. I can't know anything more about it because it's dark. I wake up and I don't want to turn a light on and wake up Leslie, so I reach down in the drawer, I grab a sock or hopefully a pair of socks, and I get this. All I know, it's good from 0 to 10. I don't have any more information. I can't narrow it down by, it's good for 2 degrees, good for 6 degrees. Nope, 0 to 10, that's all I know. All right. So this is binary stuff, and when we do electrical work, which I'm going to show you in a little bit, it's really, really important. So you'll learn a lot about this in ECE 376, which is your basic circuits course. You'll learn a lot about this in ME 368, which is your engineering measurements class, one I think is actually a really, really cool class. When you do the energy laboratory, which is also a super cool class, this one up here, you'll have to do a lot of analog to digital conversions, and that's going to become really important. And then there's several technical electives, robotics and numerical stuff, digital stuff that you could learn more about this stuff too. So it's going to show up a lot. And I think I'm moving on to, so actually I'll finish this talk with this slide. What's the point of this, right? This is the basic idea behind the resolution of of an analog to digital converter, right? You're going to measure some temperature, you're going to measure some pressure, you're going to measure some weight, you're going to measure some force, and you're going to do it with an instrument that gives you some sort of analog signal, but you have to convert that into a digital signal that your computer can read. And that digital signal is in the form of ones and zeros. How long is the number? How long is the number? Right? So for instance, if I wanted to sell bicycle wheels, and I go way back here, I need, let's do this in blue. I need 1, 2, 3, 4, 5, 6. I need 6 bits. I need a number that's 6 places long. If I want to sell wheels that are this expensive, and I want to be able to resolve it down to the single dollar, right? So to represent the number 103 accurately, right, at least to the nearest dollar, I'd need 6 bits to do that. If I want to organize my clothes, and I need to, I figure a 10-degree gap, say my useful clothes go from roughly 0 to 80 degrees, and I want to narrow them down to at the worst 10-degree bin or 10-degree window, I'd need 3 bits, right? The number has to be 1, 2, 3 digits long, right? Likewise, if I'm trying to measure some voltage, temperature, pressure, weight, force, whatever, typically you'll see an 8-bit thing, right? That's 256 bins. So with 256 bins, boy, I could narrow my clothing range down to less than a degree. In fact, I could narrow them down to 1/3 of a degree. Very, very good resolution. If I want to do even better than that, I might be able to get an analog to digital converter that has 31 bits. It's got really long numbers, which means I've got 2 billion bins, right? So, I don't think anybody has a wardrobe that requires that kind of resolution, but if you're trying to make very, very accurate measurements of very big numbers, you need a lot of bits, right? So some of the stuff we'll be using, the Arduino, which hopefully you all own by now. You should own this. Get your Arduino. That has a 10-bit analog to digital converter, so I can send it some signal and it'll break it into that number of bits. The oscilloscopes we're going to use are 8-bit converters, right? So this is, let's do this in red here. The Arduino, it's about $30. The Tektronix is 8-bit, but it's got a lot more displays and stuff built into that. That's about $200. Right. Whereas this thing right here, no displays, nothing, but it has a 24-bit A to D converter. That's about $1,500. Right. So the more precision, the better resolution you want, the more you're going to pay. Right. Okay, that's it for this. There will be another one on the basics of the oscilloscope. Don't do that. On the basics of the oscilloscope. The next video will be more detailed information about how an oscilloscope works and how and why we use them. And then I think that's all you'll need to do the pre-lab. And we'll see you in lab on Tuesday. Thanks.